So the next speaker is Steve Brookes, and he will tell us about concurrency.
Okay, thank you. Well, again, thanks for inviting me. It's a great honor to be here at Peter's 60th birthday. I think I classify myself, according to James's list, as a member of Wave Zero of the O'Hearn collaborators, because I was there. I was his external examiner in his PhD thesis, and I met him before that, even before that, when he was still a grad student. So anyway, this is work that I've been doing recently that goes back and looks again at CSL, concurrent separation logic, and my soundness proof for it. And also the recent work I've been doing on relaxed memory semantics using denotational methods. So some brief history. I mean, we talk about CSL all the time, but what was so great about CSL initially was it was so unlikely that it would work. It seemed like a bolt out of the blue. Peter had this great idea of combining ideas from separation logic, which was originally designed for sequential programs, and a Wiki-Grease logic, which is a logic for shared memory that doesn't work with pointers. And Peter's great intuition was that if you replace some of the inference rules from a Wiki-Grease, replace some of the logical ands with star, you get a completely new logic. And it works for concurrency and shared memory. So that was the great intuition that Peter had, and he came to CMU when I was many years ago and gave a talk about this stuff, and he said, I don't even know that this makes sense. It seems a really powerful idea, but does it make sense? So my minor contribution there was I showed that it did make sense. I gave a soundness proof using a form of what I call race detecting action traces. And the upshot of all this is that in the logic there's this idea of ownership transfer and a separation principle that Peter announced very clearly in his paper on the subject. And those are the key ideas of why the logic works. Making sense of that semantically, using this action trace semantics, points out that they do make sense semantically. And the upshot of it all is provable programs in this logic are race-free. And they're also safe. So that's some of the prehistory, if you like. Just to ground you, when I talk about actions in this talk, I'm referring to these are the kinds of actions that are relevant for concurrent separation logic programs. There's reads and writes to variables. So I equals v is a read where the variable I is read and it sees the value v. And then we have a writing to variables. We have lookup and updates or reads and writes to heap locations. Lock operations, acquire R and release R. Think of R as resource names, if you like. And there's heap allocation and disposal. I'm not going to use these in any examples, but just behind the talk, if you think about actions, these are the actions we have in mind. And also lock actions and allocation are treated as atomic in the semantics for this language. So trace semantics, I mentioned action trace semantics. The idea of trace semantics goes back to David Park, very early in the field. And the basic idea is that trace semantics is a way of giving a denotational semantics for shared memory programs. And in that kind of semantics, a trace is really a totally ordered sequence of actions. Programs denote sets of traces. Sequential composition is interpreted as concatenation of traces, and parallel composition is interleaving of traces. And in my semantics, traces was traces of actions, and interleaving was a form of race detecting interleaving. Now, in order to get these semantics denotationally, you have to include traces with so-called gaps. So I call them gaps. To get compositionality, you need traces with gaps to allow for the interference by things running in parallel. And the idea is then a trace is executable if it's interference-free. It doesn't need any help to get from beginning to end. So executable traces are interference-free, and that corresponds to this simple property that in the trace, each read of a variable sees the value from the most recent write previously in the trace. That idea, I mention that here because it comes back. Now, the advantage of this is that traces are mathematically quite simple objects. But the con is that traces build in sequential consistency. Well, that's an idea that goes back again to Leslie Lamport, also in the early days. Lamport said a system is sequentially consistent if the result of any execution is the same as if the operations of all the processes were executed in some sequential order, and the operations of each individual processor appear in the order specified by the program. Now, Lamport both gave that definition and almost at the same time said, but it's unrealistic, it's hard to achieve, and may not be worth the expense of designing system program implementations that guarantee it. So most modern memory models are not sequentially consistent, far from it. Instead, they allow some kind of relaxations of the program order, so the operations of each individual processor don't appear in the order specified by the program. They appear in a relaxed version of that ordering. But they don't give a linearity guarantee that all the operations of all the processors look in the same order to all threads. Instead, there's a weaker version of that. And I call that a linearity guarantee. So in this talk, I'm going to refer to memory models, and the ones I'll illustrate with, I'll give these names to. These names kind of correspond to standard, well-known, simple memory models. The SC memory model has no relaxation of the program order, and there's a linear ordering on all the atomic actions. And if you assume that all actions are atomic, you get Lamport's version. TSO, or total store order, you can relax a write followed by a read to a different location, and you can relax redundant read after write for the same location. And TSO has a linear ordering guarantee on all of the atomic writes. Not all the actions, it's just the atomic writes. PSO, or partial store order, relaxes both the same way as TSO, plus it relaxes write followed by a write to a different location. And it gives you linear ordering on all the atomic writes to each individual location, but not all the atomic writes, just a per variable linear ordering on the writes. And the common feature of all these memory models here, and all the ones I'm considering in my semantic presentation, is there's no relaxation for a read followed by a write or a write followed by a write to the same location. Okay. So my approach is I use partial orders rather than traces. Traces are total orders, linear orders. So basically I'm using what's called a POM set instead of a trace. And the idea of POM sets goes back to Vaughan Pratt, very early days again. But Pratt didn't really interpret POM sets in a way that makes sense for this setting. He had no notion of action on the state. There's also related work by Winskill on event structures. I'll come back to related work at the end. But the idea is a POM set is a partially ordered multi-set of actions. A trace is a linearly ordered multi-set of actions. It's multi because the same action can appear in multiple places in the trace. So we have a partially ordered multi-set P with an ordering less than or equal to, and each member of that set P is labeled with an action from some action set lambda. Think of a lambda as being the set of actions for CSL that I mentioned previously. And what I can do is I can provide you a denotational semantic framework parameterized by a choice of memory model, where you choose the relaxation relation and you choose the linearity guarantee, and you get an instance of my semantic framework. POM sets that build in that relaxation and that linear guarantee, tailored for the specific choice of memory model. And this construction works, all the definitions I'm going to make today work, provided the memory model is coherent in the sense that atomic writes to the same location are totally ordered. as you may have seen on the previous slides, SC, TSO, and PSO all have that property. And also, I have some simple reasonable constraints on the relaxation rules. For example, you can't relax things that would violate the coherent property. And what happens is, I can give you the quick picture now in case I run out of time and get Philippa's music coming in again. The big picture is going to be that in each case, my semantic model gives you a DRF property almost for free. DRF is this data race-free property, and it amounts to saying that race-free executions are essentially the same as SC executions. Now, race-free means if you've got two actions P and Q in the POM set that read and write the same location, and at least one of them's a write, then they must be related by the ordering. One has to come first. So that's race-free. Okay. So to outline what's going to happen is, for each memory model M, in our semantics, a program denotes a set of POM sets specific to M. And those are POM sets whose design ensures that they allow M relaxations and they enforce M linearity. These POM sets you can think of as being representations of interactive M executions or behaviors with gaps. And the behaviors without gaps, executions with no gaps, have this read-write consistency property that each read sees the value from the maximal preceding write in the POM set order. And that's a natural evolution from the property I had for traces. It sees the maximal preceding write. It's not linear ordering, it still makes sense, provided we have coherence. Now, again, what's going to happen is I can use that semantics to look again at the soundness proof I gave for CSL. The CSL assertion like this, where we have a bunch of resource names or lock names, protection lists and resource invariants, and then PCQ, that's the full version of the CSL assertions that I used in my paper on this stuff. This is James's hairy definition that he didn't want you to see. This is what it means for that assertion to be valid. What it really says is every finite interactive execution of the program in an environment that's race-free and respects the resources, which means that it respects all the invariants and so on, from a state satisfying P, respects resources, is race-free, and ends in a state satisfying Q. Okay. Now, the payoff is, to give you that semantics, any POM set can be extended to a total order. That's a well-known fact in mathematics. You can always extend a partial order to a linear order. It follows that if you use the definition of race-free execution, if you have a race-free M execution, you can extend it to a total order, and when you do that, you get a race-free SC execution with exactly the same reads from justifications and exactly the same initial state and final state. So that's the sense in which race-free executions in the weak memory model are equivalent to SC executions. There's the DRF property. And then you can use that to show that the trace-based soundness proof of CSL that I gave originally under SC corresponds to the proof that the CSL logic is sound with respect to the SC memory model I talked about here. But it also works for all the other memory models with the same general properties. So we have by one proof get many results. Your logic's not just sound for SC, it's sound for TSO and PSO, for example. So I'm running out of time already, so I'm going to have to skip the details, but this is the general structure of the semantics. If you have a memory model M with a relaxation relation rho M, the set of pairs of actions that you can relax the ordering on, and a linearity constraint lin M, the set of pairs of actions for which you guarantee that they must be totally ordered, then M POM sets are POM sets in which we have that linearity property for lin sub M. And in the definition of the semantics, which is compositional, the meaning of semicolon is not just concatenation, it's rho M relaxed concatenation, but you have to augment to complete the linearity guarantee. And then parallel composition is not interleaving, it's disjoint union augmented with the linearity guarantee. The augmentation there does some interleaving, but only partially. So if we instantiate this for SC, if you interpret all the actions as atomic, you get exactly the same as the original trace semantics. semicolon is concatenation, parallel composition is interleaving. If you do this for CSL, where there's no relaxation again and linear guarantee only for atomics, which you remember are resource actions and memory actions, that corresponds to my CSL race detecting trace semantics from the original paper, just done in this POM set setting. If you do it for TSO, then semicolon is TSO relaxed concatenations extended to a total store order. Parallel composition is disjoint union is extended to a total store order. If you do it for PSO, semicolon is PSO relaxed concatenations extended to a partial store order. And here we have unions extended to a partial store order. You see the idea is a very simple generic definition of the semantics that varies naturally across different choices of row and lin. So the benefits of this is we have a denotational semantics, we have a compositional semantics. It's modular, it's abstract. I didn't mention machines anywhere. I didn't mention buffers or anything. And it's relaxed, it's parameterized by the memory model. So we can tweak those parameters and change the instance of the semantics. And we avoid thin air issues, which plague typically approaches to try and understand weak memory or relaxed memory, because POM sets by definition have a partial order, they're acyclic. And it's easier to incorporate other things like fences and conditional atomic swap. And I like this quote from Oscar Wilde, sequential consistency is the last resort of the unimaginative. So there's a bit more about the benefits and related work. I don't have to talk about buffered state, very general abstract notion of state. I think that by having a parameterized definition like this, where you have a semantics for each choice of memory model, you can compare program executions across memory models in a nice uniform way. And because we've got compositionality, that's a contrast to some of the other approaches, and I think this method can be used to complement them. So far, again, only for a limited range of memory models, but another way of looking at it is a POM set is much more synced than a set of traces. Each individual POM set corresponds to a ton of different traces that you get by interleaving it. So that may perhaps lead to some more efficient analysis techniques, but I'm hoping somebody else will jump onto that possibility. So I have to finish off by my conclusions here. Peter's always been relaxed. Even though he never said anything about relaxed memory when he wrote that stuff on concurrent separation logic, he was already relaxing. I know WikiGreece could have been more laid back, but they never knew anything about weak memory at the time they wrote their paper. I should have been more relaxed too. Denotational semanticists like me should have and could have relaxed a lot earlier. I could have used POM set semantics in my original proof, but I didn't think that way then. Now I'm gone back and looked at it again. And at least I think I'm finally coherent. You can be the judges of that. There was a paper that Jagadish et al. Wrote in 2012 that said Brookes is relaxed almost. So it's taken me another 11 or so years, 12 years, but I'm finally getting there. And I've also got some relaxed memories. Happy 60th birthday, Pete. That's me and Pete at, remember that one? Game 7. Yeah. And that was the same year. This is actually the year I turned 60. So that just shows you how I'm even older than Pete. Anyway, thank you very much.
Thank you very much. We have time for maybe one or two questions. Yeah.
So Pratt had a definition of parallel composition of POM sets.
Yeah.
And this is not it.
Pratt's definition was just disjoint union.
Can you comment on why you don't use Pratt's definition of...
Yeah, because I want to tailor it to the relaxed memory setting. And Pratt had in mind the idea that a POM set can always be linearized. He said it's equivalent, a POM set's equivalent to its linearizations. So he was thinking about the SC interpretation of a POM set. It's just an abbreviated way of summarizing a set of traces. But if you want to do weak memory or relaxed memory, you have to move away from essentially using traces all the time.
But I think even for sequential consistency, Pratt's definition doesn't work.
Yeah.
Because you need disjoint plus extend.
Right.
Okay.
Yeah, Pratt's approach was beautiful and elegant and simplistic, but he didn't actually apply it to any real programming languages. He didn't talk about actions as having any semantic content. They were just purely symbolic.
Any other questions?
Thank you so much, Steve. Great talk. So you mentioned that so far you cover SC, TSO, PSO, all the ones that are reasonable. They don't have this load-to-store load buffering, essentially. But what about memory models such as the release-acquire fragment of C11, where you don't have these crazy out-of-thin-air problems, but it's still not exactly TSO or PSO?
That's next on my list to look at is release-acquire. I think that should be reasonably well behaved enough. Maybe I can extend the approach there.
So you think that...
I think so, yeah. They still have the guarantee that, I think they still have the atomic rights per variable,
yes,
totally ordered.
Yeah.
Okay, so let's thank the speaker.